Well, hello everyone. Good afternoon, and we hope you all are staying safe and healthy. Thank you for joining us today for our webinar on responding to issues. So this is actually part of a grant that was funded by the National Endowment for the Humanities, and so we wanted to thank them for their support. This is our second series on environmental data analysis, which is designed for institutions with a year or more's worth of data, really ready to start evaluating spaces and determining steps forward. So if this describes you, that's wonderful. If you would like more of a refresher on some of the other steps to this, we invite you to check out Series 1 as well on environmental management. You're welcome to ask questions as they come up, which you can do by typing in the chat box that you see on your screen. If you're watching this as a recording, have a specific question, or something comes up later, you're also welcome to email us directly. Both Chris and my email addresses are on the final slide of this presentation, as well as available on the IPI website. So this webinar is being recorded and will remain available for at least a year. As I mentioned before, this is one in a series of 3 webinars. So if you missed the previous 2, please visit ipisustainability.org/webinars, and you can view those previous 2 webinars either as a recording or download the presentation in the location that you see marked by the red box there. So in the first webinar on understanding fluctuations and equilibrations, we looked at examples of temperature and relative humidity and looked at how the rates of equilibration, the change, the extent of change, the rate of change, and repetitions could impact preservation, and when they represented risks and when they did not. And for setting appropriate parameters, we looked at the role of standards and how to determine what is possible and what is ideal, and use that to inform setting your parameters at your institution. So now that we kind of understand what the data is telling us about risks, and we understand our goals for what we would like to achieve from a preservation standpoint, you'll know when you have an issue. So now we'd like to talk about the next step, which is really how to respond. And in today's webinar, we're going to cover both the good and the bad of response procedures. So before we get into it, I just wanted to give a brief introduction to IPI for anyone who may be unfamiliar with us. IPI, or the Image Permanence Institute, started in 1985 studying film and photographic materials, and seeing the importance of environmental conditions on preservation, expanded its scope to address this concern for more materials, and to do so in a sustainable way. So my name is Kelly McCauley-Krish. I'm the Preventive Conservation Specialist here at IPI. My background is in art conservation, and I work here on the environmental consulting team as well as on research projects to help make storage and exhibit spaces more preservation friendly and more sustainable. So I often represent the collection side and help work through what would be the best parameters for them. And joining me today is Chris Cameron, who is the Sustainable Preservation Specialist at IPI. Chris's background is as a former facilities manager, and he's HVAC trained. So Chris represents the mechanical side to our analysis, and he's able to tell us what is possible with our existing equipment and what changes might be needed in order to improve preservation and sustainability. So with that, we'll get started on today's topic. And first, just want to start with kind of a distinction here. I think probably one thing that we're all somewhat familiar with is the idea of incidents. And so those are kind of an event or an occurrence. They have a beginning, middle, and end, even if they feel very drawn out. So a good example of an incident is a flood or a fire, something like that that's, it really stands out as an event. And so this is different than an issue, which is really more of a problem or a difficulty. And these may be gradual or sudden, but they're kind of continuous problems. And so examples of issues are really more heat loads on a space, or a cooling coil is failing, there might be occupancy. So things that have to do with the space, the mechanical system, or the operation, rather than as compared to an incident or an event. So what we're going to be covering today is really more focused on issues and less so on incidents. So I just wanted to kind of clarify that. We're not going to be covering how to respond to a mold outbreak or anything like that, but we are going to be talking about what to do if you see high relative humidity. So when we start talking about issues, first you'll say that there can be multiple potential causes or even a combination of factors. So that makes it really important to try to get at the root of the issue and to address it in the most appropriate way possible. This is the basic outline that we'll be talking through today in terms of the steps of how to respond to an issue. And of course, that begins with identifying what the problem is, which we'll do through a combination of data analysis. You might be wondering why you've been collecting data all this time, and here it's a chance to put it to work, as well as through evaluating the space in the system. We'll talk about how to make a change by communicating and developing an action plan through your environmental management team. And then, of course, after we've made that change, we want to see if the changes we made were effective and positive, and if not, what are our options for modifying them and creating the kind of environment that we'd like to see. Okay, so we're going to start now on data analysis, and I'm just going to walk through some of the questions that you'll want to be asking yourself when you're performing data analysis. So the first one is really what is happening and what is the extent of the issue. So if we look at the example of the data here on the right of the screen, we can see that the relative humidity of space A, which is shown with the blue line, climbs above 65% in the summer, and in fact is actually getting quite close to 80%. So we know that that's an issue because it's definitely putting us in a category where we'd be concerned about mold germination, metal corrosion, and many other forms of deterioration that are driven by relative humidity. When we compare it to other spaces to ask where is it happening, we can see that even though the red space may have a high relative humidity around 60%, it's really not displaying the same pattern as space A, and certainly the yellow space as well is not having relative humidities anywhere near the same as space A. So this seems to be a fairly localized problem for space A. Okay, so then we want to know when is it happening. And so the more data we have, the longer history we have of it, it's easier for us to determine the onset of an issue and look for any patterns or trends. And so here you can see that we've pulled up the previous year's data as well, and we can see that the same issue presented itself last summer. So this is useful to know because now we know that it's not necessarily a new issue that's come up, but it's something that we're seeing recurring. So it tends to indicate that if it was a change in operation, it happened a while back. It's not something that we did recently that is affecting it, but it probably has something more to do with a longer-term operation of the space. All right, so then we want to move on to looking at the other parameters. So our initial concern was with relative humidity, but we know from previous webinars that relative humidity is really just a result of the temperature and the dew point. So we need to look at those and see which one is causing this problem. And so here we're comparing the dew point of all three spaces with the dew point outside and outside of the building. And you can see that in general, all of the spaces are following the same trends in outside air. So as the moisture goes up in the summer outside, the moisture is going up pretty much the same amount in all of those spaces as well. And when we go to look at temperature, we can see, though, that there is a difference here in temperature. And space A is a lower temperature than that of the other spaces. So because they all responded to the outside dew point in the same way, we know that it's not necessarily a difference in moisture that is causing this high relative humidity, but rather it's a result of the same high moisture but a lower temperature. And so because of that inverse relationship, those higher temperatures in the other spaces is able to artificially suppress the relative humidity in those other rooms. So this is just kind of an example of how when walking through the data analysis, even just looking at the data, we have a sense of what the problem is. It's not necessarily that there's a moisture load in the space itself or the fact that something is broken on the unit serving this room only. It seems to be that in general the spaces are kind of receiving the same conditioned air, but the temperature differences is what's causing the relative humidity difference. So that concludes just one example of how data analysis can inform us about the problem. We're going to move into mechanical and space evaluations next and go over some other lessons learned from these other examples.
So one of the things IPI covers, or likes to talk about a lot, is really knowing your mechanical system, evaluating that system, knowing the air that it's producing, how it's creating that environment for your collection. And when doing any form of mechanical system evaluation, we like to start just addressing the soundness of the unit. What does that unit look like? Is the unit structurally intact? And we mean, are there holes in the unit? Are there doors or openings in the unit that don't close? And we've seen that a number of times where, again, go back to a door, where a door gets propped open on a unit and the air handling unit is just pulling in air from wherever. And that will negate any of the work that has already been performed by the unit and wind up giving, lower or higher relative humidity downstream because of that. Do you have water inside a unit? It's actually something we've seen quite a bit. Standing water in an air handling unit can be common because if a unit is dehumidifying, you're going to have some condensation in there. However, we've seen anywhere from 2, 3, 4 inches of water stuck in a unit. The drain gets plugged, it's just not leaving. What happens is you have what's called an adiabatic effect. That means that air that has already been dehumidified is passing over that standing water and will collect that moisture back up as it goes, bringing that moisture downstream. So you'll wind up having a higher humidity downstream than you'd like because there's that standing water trapped in the unit. So really, this is just two of many things, but really assessing as you're looking at mechanical system, what's it look like? Are there any deficiencies we should be aware of? Are there any problems? And then also doing some data collection, putting additional monitors within the air handling unit. We'll cover that in a few minutes, or in a few seconds. Really just addressing each point throughout the system and getting an idea. We want to check in the locations, not only of the loggers in the space, of our loggers in the mechanical system, make sure we have them in the right position. We're getting a good air mix, if you will call it, but also a good reading. Do we have a proper location in our space to read really what's happening? We're not reading a microclimate or so that's giving us a false reading. So we'll start before you do any form of going near your mechanical system at all. I can't stress really being safe, being careful around this equipment. Always follow your facility safety procedures. Make sure you have a facility staff with you, permission from the facilities to go in there. Make sure you're as careful as can be. There's things in the mechanical room that can hurt you. So really be as careful as possible. Make sure you have that permission. Carry a cell phone or flashlight with you, just in the off chance, God forbid, power goes out while you're down there. You have some way to see or contact somebody, and leave everything exactly as you found it. Don't touch anything. There's among many other rules, but these would be my first and foremost for going in there. But really being as careful as can be when going near this equipment. So when you're going back to the evaluation of the air handling unit, really doing the in-depth analysis, just some questions to answer while you're looking at it. Some questions will be answered while you evaluate that data. Is there a change to the amount of outside air we use? We'll go over some data a little later that will really show how the percentage of outside air can play a factor in a collection space. How much you were really going to use is really going to have a say in the dew point or moisture content in the space. Location of the intake, where that could be. My own experience as a facility manager years ago, the outside air intake for a medical facility was by the loading dock, and there were two problems with that. The first problem was anytime a vehicle pulled up to unload and was sat idle, the outside air was pulling in exhaust from vehicles, so it was no longer fresh air. We now had some polluted combustion from vehicles, and it was also the smoker's door. So when smokers would go outside, people within the facility could smell their cigarettes. We wind up having to move that. So keep in mind, the location of the intake could play a major factor. Status of the cooling coil, when your chilled water gets turned on, if there's a clog or issue with the chilled water, again, we'll show an instance of that later when we evaluate data. When you evaluate a mechanical system, it's also important to get an idea of where does your ductwork travel, what does that ductwork look like. The layout of the ductwork can be almost as important as the work that the mechanical system does. And I hate to keep using the phrase, but when we do data analysis, I'll give some examples of some ductwork issues from where the ductwork either traveled or problems with ductwork going through space that could cause issues within the collection space. And really getting to know that downstream equipment, what is downstream in your collection space, how could malfunctions or issues with that equipment really play out, what will that mean to your spaces or collection if that happens. So when we talk about adding data loggers in a mechanical system, this is just an example. Not every system clearly looks like this, but it's just to give a rough layout of what typically we have done in the past. So going in here, we would start, say, this is enabled, but say this would be our return air. This would be the outside air for the unit. So we would put a data logger on each of those because we would want to record the conditions separately of each of those points as it comes in. And then after our filter, we would put a data logger here, and this filter would represent the amount of outside air and mixed air that we're seeing mixed together. And we'll show some data, give you an example of how we read that, and then from the mixed air, we look at the cooling coil data. So we will be looking for the pre and post conditions. What does our air look like here? What does it look like? What does it look like after the coil? So what kind of work are we performing? You may find out if you're in a cool climate and then in wintertime that you may be running your cooling coil in the wintertime when you don't need to be using a lot of energy excessively. After the cooling coil, we could either put, this is an either or, it's not a both, putting it after the heating coil or either after the fan in the scenario. Again, looking for that pre-post conditions. We now know what the cool air is. After that, what kind of heating are we doing to that air? What kind of how much energy are we putting into that air? What's the temperature we're raising it to? And then sending it down to after our humidifier, how much are we humidifying the air? What are we changing? Each one of those steps, we're trying to evaluate at what point work is done to that air, how much work we're doing to really get a picture of the environment we're creating, and even at times some unannounced errors or energy waste that we can come across. Give a quick example in here. This is not just in the unit, but even putting them downstream, basically part of the unit, getting them right on the face of the supply or right on the face of the return diffuser. So we're getting that direct idea, what's being delivered right into the space and what is the air leaving the space. A lot of times this can be compared to maybe the sensors that we see for the actual mechanical system to what the mechanical system thinks it's delivering compared to what we're actually delivering in the space. And then just an example here, going back to the unit, where we'd put them. Here you can see we put it right on the face of a cooling coil, here attached right to the face of a humidifier. These little blue loggers, they're conformal coated. They're meant to take some harsher conditions, some conditions that mostly a hobo or a PEM might not be able to take, and really record that data. We have a question about what does HVAC mean? It's heating, ventilation, and air conditioning. I apologize. So we're really trying to record the conditions that are coming directly off of those. And these little loggers, again, it's called an ACR log. The brand is called ACR. It's a conformal coated logger that's meant to really be in those harsh conditions and record that data so you can see firsthand what's happening there. If you want a little more information on data logging, so I don't want to go too much into it, the guidebook is available. The website that you signed up for, or you went through the sign up for the webinars, has a resource page. The guidebook is available for free download there, and I believe the original book before this is available there as well if you'd like to download that also. So we'll get into an example real quick. Talked about evaluating that outside air. So here we have a couple different loggers. We have the data for our outside air, which is this yellow data you'll see here. Our mixed air at the unit, which is a combination of this return air, which is teal, and the outside air, which is yellow. So whatever the combination of these two would be our blue line. And then our red is what is being read on the shelf inside the collection space. So going back to look at that, we have the condition we're actively delivering, or actively experiencing in our collection is the red line. And then the collection leaving is this teal line. So we're probably at about 72 degrees in the space, and then we return about 68, so there's a little bit of a temperature loss. So with that temperature loss, it's now pretty cold outside, and it's an unoccupied collection space. And you can see here, we're actually using a fair amount of outside air and losing some temperature. I lost my cursor there. Losing some temperature with that. So this air, this blue line, to go back out to the collection space has to be heated up to about the red logger's condition. So all this is work that has to be performed to make it back usable for the collection. Again, it's an unoccupied space. Having worked in this facility, we talked to the facility staff, and we were able to find out that they were using a very large amount of outside air for an unoccupied collection room. We were able to reduce that, save a little bit of energy that's being used, and narrow this gap a little bit. So we're not lowering that temperature so much and reheating it, losing some energy in that process. So we also recommend doing space evaluation. We're not asking anyone to be architects, engineers. We're really just trying to help you get a better understanding of what your space looks like, what's really happening in the collection space, how the environment is built, if you will. Do you have, looking at the envelope, do you have passive vents in the walls? Are they within your ceiling? They can play a factor in the conditioning of a room. Do you have gaps around doors, or are there former windows? We've had former windows in collection spaces, even boarded up and insulated, that have been acted as heat issues or heat sinks within a space. And also, identifying things that can place loads on a collection space. Surrounding spaces, if you have a landlocked room that you're trying to condition to, say, 50 degrees, the room is poorly insulated and the halls around it are being conditioned to about 70 degrees, the 50-degree room will lose in the sense of it will struggle to hold that temperature if it's poorly insulated and wind up having a heat load from the surrounding space. So you'll constantly have that heat load being placed on that cooler room without the ability to really fight it off. And solution there would be to insulate the walls better. Another thing that sometimes that places heat loads into space are radiators, some water source heat or electrical source heat that we have at times seen not turned off in the summertime when it should be off, that cause extra loads within the space. Oh, sorry, there we go. And really just assessing your building floor tightness, looking at your roof, your walls, the windows, foundations. Get an idea. If you look at this image here, this space wouldn't be one that we would expect to hold a really good tight condition. You can see the framer on the window is very thin wood. The glass itself is single pane. There's some gaps over here, just a little bit of daylight that comes through, a highway for pests, unconditioned air in the space. And even looking at the ceiling, it's just basic wood. It's not insulated very well. So if I was to walk through this, that'd be a good sign. We are not holding a tight condition. Even if we were aiming for human comfort in there, it would be a trouble because we'd be losing that condition constantly. So lastly, one of the things we're going to really look at here, some things that really affect the facility are sometimes not by design and mechanical system or layout of the space. Sometimes it's on our own operation, and that could be the occupancy. Some human occupancy in space has added significant amounts of temperature. Even if it's a highly occupied space, can add moisture as well. As people breathe out, just their presence in the space will add some moisture to the collection. We say that heaters, humidifiers, they add basic equipment. If you have coffee pots, copiers, those things can add heat to a space. Again, going to the operation, the doors propped open, leaving doors propped open on spaces. There is a rare book room that we worked with in a library that wanted to feel inviting to people or students in the library to come in and look at the books. So every day they would prop the doors open at 8 o'clock. And in doing so, they're losing the condition that they were working to create for that rare book room for the entire time the doors were propped open. Leaving lights on, lights can add, we've seen it, lights add 3 to 5 degrees in the collection space, so that all adds up. Most importantly, one of the things I can't stress enough is make sure there is nothing impeding the airflow in your collection space. We're not blocking any supplies or returns. That tends to be a huge critical issue. It happens. A lot of boxes stacked right up to the face of a supply or return where there isn't a good airflow. You want to have at least, we typically tell people about 2 feet, 18 inches roughly in there of a space around a supplier return grill, so you really can get that air mix and you're not blocking anything. And make sure that the dampers are open. You haven't shut a damper down or even had an instance where a fire damper has broken free and blocked off the airflow for a space.
Okay, so hopefully now, now that we've gone through data analysis and space and system evaluations, you can see how this would all help us to identify the problem, or at least have some ideas about what could be causing or contributing to any issues. So whether that's from a load on the space or from some kind of mechanical system operation, we can hopefully start to work towards those solutions. So now we're going to move on to the next stage, which is making a change. And this heavily involves communication and developing an action plan. So ideally, if you're at this point in the series, then we hope that you have an environmental management team in place. If not, there are some other resources we can point you to towards creating and developing these relationships. But ideally, addressing these issues is really part of that team's activities. So whether you have a standing meeting or you communicate through email, you should have those people involved in the process and be able to reach them to discuss these issues. But like any time, effective communication is really key. It's important to be clear and concise, especially because everyone has limited time, and so they want to see exactly what the issue is and what needs to be done about it. So a good example of this is the set point change. Sometimes people may communicate with facilities and ask if a space can be made warmer, say for example, and they may make the change, and you might see it in your data. And we'll see an example of this in just a few minutes. So that's the kind of thing that if you see this change and you're able to communicate effectively with facilities, you may be able to pinpoint what happened exactly and address the issue fairly quickly, rather than trying to track down if there was something else at play. You can pretty quickly attribute the effect to the cause, and so that can be a real time saver. And it also helps you to address some of the other issues of how people are asking for the set point changes and when it would be appropriate, and give facilities some backup to why they may not make a change, so that they're not constantly responding back and forth to temperature issues. The other main part about this is just the importance of maintaining documentation. It's difficult over time, and especially as people change in their positions, to keep track of exactly when a certain issue came up or what changes were made. So you may have found that the outside damper, you had changed the percentage of outside air that was being brought into the facility, and you made that change on this day. But maybe next summer, all of a sudden you realize that it's a lot more humid in your space than it was the previous one. And it's because maybe that outside air damper was never closed back down to a lower percentage. So it's important to keep track of these things, and it can really provide important documentation for informing the data analysis and the action plan. So when we're talking through these things with our teams, one technique that I thought was really helpful that I wanted to share with you all, I learned through a webinar by the Indiana Historical Society, and they suggested using the 5 whys of strategic planning. And this is really meant to, we understand that there's an issue, and so we want to get at what is the root cause of this. We may have started to do this through our evaluation and data analysis, but we want to make sure that we're addressing the true cause of it. So an example of this might be if we saw an increase in relative humidity. So we ask our first why, And because we're maybe looking at the data that we've collected from monitoring in the mechanical system, we can see that the supply air relative humidity also increased. So why was that? And looking at the data from the mechanical system further, we can see that it was because the cooling coil was not dehumidifying enough. So we weren't removing enough moisture from the air at the point where we were able to do that. And so all that moisture is being sent down into the collection space. So why is that? Well, it could be that in talking with facilities and looking at the mechanical system with them, we realized that the cooling coil is clogged. And the why for that might be that preventive maintenance was removed. And often the reason for this, so that final why, might be that funding was cut. And usually preventive maintenance is one of the first things, sadly, that goes and can often cause some major issues with this. So we know then that the proper steps are really, we need to address the funding for our preventive maintenance, and we need to get that cooling coil clogged. So you can see how this is helpful, because if we stopped at the point where we just discussed that there was an increase in relative humidity, there are many possible causes of this, and so we wouldn't necessarily know whether it was an issue with the space itself or the mechanical system or some other kind of issue going on. And if we only knew that the cooling coil wasn't dehumidifying enough, but we didn't know the true cause of that, we may think that it might be equipment failure or the equipment that wasn't designed properly. So we might be looking, thinking that we need a full system replacement, when in reality what we need is to restore the preventive maintenance. So I encourage you, if you find that technique helpful, to use that in your team meetings to evaluate issues as well. Okay, so just to kind of give you a sense of what we would want to cover through our communications, there's really two main questions that we need to ask ourselves every time an issue comes up. And the first is, does it need to be addressed? Because we may notice something's different and we want to note it, but it may not be something that needs immediate attention. And so from the collection side, this is best answered through our risk assessment and through applying the research from environmental studies on how that impacts collections. And again, I encourage you to look at the previous webinars in the series if those are things that you would like to learn more about. Or it could be something that other aspects of your institution's operations come into play. For example, does it need to be addressed because there are loan agreements that need to be upheld, or are there human comfort concerns in gallery or office spaces? The second question is really, can it be addressed? So just because something really is a concern and a risk for the collection, the capabilities of your building envelope, mechanical system, the layout of the space and the ductwork and its uses may limit your ability to actually address an issue effectively. An example of this where our risks might have to be balanced is, you can see the graph on the data. The graph of the data on the right is from an institution that saw the relative humidity was increasing to 60%, and actually the trend was to continue increasing. And so for them, this did represent a risk that needed to be addressed, and they did not have any complicating, loan agreements or human comfort concerns, but they did need to address this from a collections perspective. But unfortunately, due to limitations in the mechanical system, it wasn't possible to increase dehumidification. So what they ended up having to do was to increase the temperature to artificially lower that relative humidity. And here you can see how that relative humidity starts to drop back down. Starting in about August to September, we see it start to come back down. So in that way, they arrived at the conclusion that they were willing to trade off a little bit of short-term chemical decay in order to keep the very real risks of mold germination and metal corrosion and other factors under control. Okay, so once we started to talk these things through, we want to develop an action plan. So if it's something that is a basic change, for example, the set point change or a closed damper, this may just be a meeting where people go away with certain tasks assigned to them, and they're all clear on which direction they're going to take, and you can return and make sure that those that the steps that were taken were effective at your next meeting. For longer-term planning, though, that tends to involve more stakeholders across an institution in order to establish your goals and priorities. And it's really important to sequence all these actions with respect to other plans. So, for example, if you're working to address issues with an air handling unit, but your long-term plan, is maybe to move to another collection space on a different floor, maybe your money is better spent looking at other collections care issues rather than trying to address a space that will really be, only for another year or so. And this is really because additional factors will come into play, especially cost, when we start talking about long-term planning and issues that really require capital investments to address. Okay, so if these action plans should all be part of your institution's long-term preservation plan. If this is something that your institution doesn't have and you'd be interested in learning more, I recommend the connectingtocollections.org. They have a number of resources on preservation planning, as well as great resources on many other topics. So this is actually just an excerpt of an action plan that was developed by one institution, and so obviously there are many other phases that are part of this chart, as well as other rows that address the building envelope and collection needs. And so each section is has a specific point person assigned to see through each of these steps, and then the steps are laid out and ranked and kind of color-coded in terms of their impact on collections, and so their importance to be addressed. So this is just an example of what you might kind of come away from these meetings with. Okay, so the final stage is testing. We have a couple recommendations for how you would actually, when you go to make those changes, what you would do for testing. First of all is you want to start small. So starting small allows you to build on successes or address concerns early on. The other thing is to consider the timing and the duration of a test. You may want to do it when outside conditions are less likely to have a negative effect on collections, or when occupancy would be less of an issue. Changing one variable at a time is also important because it allows you to gauge the impact of each step. If you make 5 changes all at once, if the issue comes up again or something else needs to be changed, you won't know what step needs to remain in place or be emphasized in order to address the issue. The other thing is when you've made a change, you want to evaluate more frequently. You don't need a year's worth of data to see if the change you've made has been significant and is something that you want to keep, although it may be something to keep in mind as the seasons change if you're seeing any differences. So the graph on the right here, the blue and the teal lines represent a collection space, and then the red line represents a data logger that was on a shelf in the collection space directly across from a window. And you can see that there's definitely a lot of a temperature load that's coming into the space from that window, and it is ultimately affecting the temperature in the collection space as well. Whereas previously they might have been trying for, almost a 65 or a 60 degree temperature, in the end they're closer to a 72, 73 degree temperature. So what they ended up doing was blocking those windows. So again, starting small and making one change, and you can see that change right around the 23rd, and those fluctuations in temperature definitely start to lessen, and we start to see the temperature gradually come down. So, whether they would want to implement other strategies to bring that temperature even further down and back closer to the 65 or 60 degree temperature would be an option to discuss. But generally, we want to see, did the situation improve somewhat? So we may want to take additional steps, as is seen here. Perhaps it returned to its previous state, which we assume is, is probably somewhat acceptable at least. Maybe it even got better than it was before. But certainly, if there was no effect or a negative effect, we need to talk through, can further measures be taken, and do we need to modify it in any way in order for our steps to be effective? Okay, so next we're going to look at some common preservation and operation issues and show you kind of how they look in terms of the data and talk through some of the potential causes and what might be ways to address those. So the first one is a change in temperature. So here you can see that the temperature has increased in a very short period of time, that we pretty much go from, you know, from the 8th to the 9th, we're increasing in temperature from, you know, about 70 degrees up to about 73, 74 degrees. And so from a preservation standpoint, we know that we're not necessarily concerned about this increase in temperature if it's only maintained for a short while. But we would be concerned if this is a new setting that we intend to keep, because over time that loss in preservation quality is going to result in a faster rate of chemical decay. So a change in temperature that is sharp like this, that is over such a short time period, often indicates a change in operation. So this could be an example of a change in set point, or possibly even a mechanical failure, depending on how high the temperature gets. Usually when we see the effects of loads from other spaces, they tend to be a little bit more gradual. So a drop can also be a problem, not from a preservation standpoint, because we know those lower temperatures help to preserve collections, but more because of the impact it can have on relative humidity. So if we see these sharp changes in temperature, we definitely want to start having those conversations with facilities and those who are occupying the space, to ask if there's, you know, if there has been any change in operation and what the reason for that was. An increase in relative humidity. We know from the third webinar in the series that our concerns with relative humidity really have to do with sustained high levels that are long-term and recurring. So if the relative humidity here were maintained more at a 50% or even a 60% over the summer, we maybe would be less concerned about this increase. But here we're starting to get very close to 80%, and so again, like we mentioned before, it's putting us pretty solidly at a risk for mold germination, metal corrosion, and such. Increase in relative humidity, again, is going to be a result of one of your other two parameters. So in this instance, we definitely want to check our dew point. If we see that it's following closely with the outside air, if we don't have a mechanical system, we may have limited options, and we would want to address any moisture issues that we can in the space, whether that's redirecting gutters or fixing leaks, and we would potentially want to look at increasing the heating to the space to try to potentially lower that relative humidity. If we do have a mechanical system and we see that either the temperature has been lowered due to a set point change, or we've seen a loss in dew point, that's an issue that we'll be talking about on the next slide. Okay, so this increase in dew point comes from a space that had a cooling coil that was initially designed to provide a 45-degree dew point. And if you remember from previous discussions, dew point is what is going to determine the combination of temperature and relative humidity that you can get within a space. So the lower the dew point, the better combinations of temperature and relative humidity for preservation that we can achieve. And the higher it gets, the fewer options we have for creating a good preservation environment. So even though we were initially designed for a 45-degree dew point, you can see that as far back as our data goes, we were really getting about a 50-degree dew point. We would expect some loss, you know, so maybe it was never operating fully as intended, but it was better. And if we fast forward a few years, we can see that instead now we're operating at more of a 55-degree dew point. So this actually can have very significant impacts for the temperature and relative humidity, and therefore the long-term preservation of collections. Usually when we see this gradual increase in dew point over a period of years, this tends to indicate that if you have a mechanical system present, that there's a gradual failure of the cooling coil. And so you may want to look at that component in particular and see if either preventive maintenance needs to be performed or possibly even replacement. And the final preservation issue that I want to talk about today is stagnant or stale air. Obviously, this is really more of a complaint we get from the human occupants of any collection spaces rather than from data analysis or from what the collections are telling us. But it can be an issue because it often leads people to prop doors open and make other changes to the space's operation in order to get that air moving. So the most common cause of stagnant or stale air, it means that a damper has been closed. And so that is the silver box here, that rectangular box space there. You can see that there's metal blocking it. So this is a closed damper. So that means that all the ductwork that you have going from your mechanical system into the space, it'll have dampers to modify the amount of air that's going in. And if they get closed completely, the air that's being created by your mechanical system can't be delivered to the room. So you get that feeling of stagnant air. So in addition to dampers that are related to the airflow being closed or closed from their full position or intended position, as Chris mentioned, there can also be fire dampers. These are put in place in case of an emergency so that they can drop closed and prevent any smoke and soot from circulating throughout the building. Sometimes these will fall closed over time, or something might trigger them that you may not be aware of. And so as long as these remain closed, again, airflow is not getting to the space. So if you hear about complaints about this, it might be a good indicator to look at some of those dampers.
All right, I'm going to wrap up here with a few examples of some operational issues that we see. Just some examples of some data, some analysis, and how what we were able to determine from that. First one is a temperature load on a space. And this is one of those, most of the examples that I have are all unannouncing. They're just things we were able to determine by evaluating the data and really getting an idea of what's happening in the space, or what's happening in the mechanical system, as well as the space. So if you look at this data set, both the teal and the red lines are the supplier for the space. Like I showed earlier, getting a data logger directly on the supply vents and directly at the return vents in the space, getting an idea for what's going into and out of a space. So here we have, we're supplying about 56, 57 degrees for the collection space, but we're returning 70 degrees out of the collection space. And what we're able to determine when we're looking at this, really get in there. First of all, from these two lines down here to up here is almost 14, 15 degrees that goes back and the mechanical system has to remove. So we go, what is causing that much of a heat gain? It's a significant heat gain. And when you walk through that collection space, you don't feel that. You don't feel any major humidity, any major gain. So this is something that would not have been known was occurring until we really started to delve deeper into that. And what was happening is the room had what was called an open plenum. So the air from the room was returned up into an open ceiling with no vents or ducts, and then pulled out of an actual vent back to the mechanical system on the wall. So that at the mechanical system was where our logger was, at that vent. So somewhere from leaving the room and then getting to the return vent in the wall up in the ceiling, we were gaining that 15 degrees. And I brought it up, I mentioned earlier, knowing your envelope, knowing how tightly sealed it is. That room itself had gaps from old pipes, old ductworks in the surrounding spaces. Those surrounding rooms were being conditioned to, about 70, 72 degrees. And those were playing a major factor. That cool air got brought up in the ceiling. It was mixing with air from halls, from the room above, from wherever, that was raising that temperature. So that cool air coming out of the room, that condition was lost and brought back to the unit warm. And that mechanical system then had to reduce this temperature again using more energy for this condition. And it's something that the staff and the maintenance didn't really understand or know what was going on for that space. So we have an example here that of moisture load in a space. Sometimes it's not always temperature can be an issue. Sometimes it's moisture. When we evaluate a collection space or multiple collection spaces, multiple zones for a facility, one of the things we look for is called a dew point signature. And different dew points, like significantly different, like these two, would tell us that it's a different mechanical system serving the space. What we would look for, maybe say something more like this on this far end, this October data, where dew points overline over each other would tell us that's the same or most likely similar mechanical system serving those spaces. Well, having worked in the space, I can tell you that that is absolutely the same mechanical system serving one very large gallery exhibition space in a museum. It's a rather large gallery. This blue logger is at one end and the red logger is at another end of this gallery. So from one end of a large gallery, we're seeing a almost 8 to 10 degree dew point gain, which is really significant for that space. Really concerning as well, because that's, you know, what they think they're conditioning their gallery for. They have a major gain of moisture. So this is one where we had to step back and say, what does this cause? We evaluate the mechanical system, and one of the things we mentioned was that downstream equipment. When we look at the downstream equipment here, and after the mechanical system, after our last data log in the mechanical system, there is no other downstream equipment. So nothing from the system, all the air leaving the system agreed with this blue line. So if it agrees with the blue line, what's the cause? We look at the space, we look at the envelope, we look at our galleries or rooms, and a few, just recently, within a few months or maybe a year beforehand, they had opened a butterfly garden exhibit, and to condition the butterfly garden, there was all the equipment, HVAC systems that were installed, and it was on the other side of the wall for this space. In doing so, the moisture, when you go in the mechanical system that served that butterfly garden, is a very hot, humid room. That moisture was coming through the wall. They didn't add any vapor barriers. And even the ductwork, as I mentioned earlier, that traveled through there was leaking in a few spots. There were a few finger-sized gaps that just weren't sealed properly, and were leaking really hot, humid air up into the ceiling, and that humidity was sticking inside the room. The HVAC system could compensate for the heat, but not compensate for that much moisture gain. So that's why we saw this significant moisture difference in the two. And here you see about the time where they started to address adding that insulation, adding that vapor barrier, that insulation tending to the walls, and sealing up that ductwork to really prevent that from being such an issue. In a major scenario like this, we typically don't always like to recommend getting dehumidifiers in the space. We'd like to try and stay with that only as a last ditch resort. But if you find yourself in a situation like that where it's such a massive gain, at times that is the better part of it, if you will, where you may have to do that to really help reduce that humidification short term until you can get that answer.
And here I just wanted to, we had a comment come in from Barbara that said, I thought increasing temperature to lower humidity was dangerous, especially if you have a mold outbreak. The humidity is difficult to lower fast enough, and increased heat can aid the growth of mold. And Barbara, I think you're absolutely right in terms of how difficult it is to remove moisture quickly. In terms of the previous example we showed, one of the reasons that they took those steps was because they weren't currently at a mold risk, but they were trended in that direction. So I think your comments about balancing temperature and moisture are definitely ones to take into account. And so it really just depends where you are in that stage. If you've already had a mold outbreak, there may be other steps that you need to take as well, but your options might be a little greater if you are just having an increase in moisture.
All right. So just two more examples here. One is using the use of incorrect set points. Again, this is something that wouldn't be directly self-announcing. Here you see some outside air. We have the yellow line, which is typically what we would expect. We have our cool winters, our warmer summers. So the swings seasonally are exactly what we would expect to see. What we see for the interior spaces we're actually running warmer in the wintertime and much cooler in the summertime. While it makes some sense that we want to warm the space more, we want to cool more in the summertime, it's actually, to an extent, it's counterintuitive to our energy use. Where in the wintertime, we might be able to make better use of the cooler conditions, get some passive conditioning. If we lower the temperature without changing the dew point, or if we lower that temperature a bit, we can raise that relative humidity and use that to help balance out, do less humidification and provide a cooler, better condition for the space. And consequently, for the summertime, this is a lot of work for the mechanical system to perform. So maybe we don't stress this unit as much, driving it down to 60 degrees. And even for a gallery, it can be kind of cool if, at that temperature. Maybe not supplying that temperature in the winter, in the summertime, if we don't have to, let that drift up a little more and fight that condition a little less, resulting in less energy use. And one of the last examples here is this heating and cooling example. Again, this is another one that was not self-announcing at all. Working with a gallery, working with a collection storage space. I'm sorry, we have 4 loggers. We have 2 that were located on a shelf on either side of the room, shelf A and shelf B. You see that those 2 loggers, temperature-wise, completely agree with each other. They're 72 degrees, and they're perfectly happy. They're almost right on top of each other. But however, we have a data logger within each supply, one reading the supply on one side of the facility, or that comes from one side of the facility, one comes from the other. One supply was almost 90 degrees, at times it was 90 or more, and the other was anywhere from 60 to say 66 degrees in there. So you ask the staff and they walk through and they knew of warmer or cold spaces. There were a lot of fans there in the space mixing the air. They knew of a lot of cold and warm spaces and microclimates, so to speak, throughout there, but they attributed them to either outside walls at times or, boilers or pipes through the floors. There was no I think it might be this reason or that. And then when we really started to collect this data, even walking around first before this with an IR camera, we were able to identify one side of the room was being heated, or one duct coming from one side of the room was being heated, and the ducts coming from the other side were being cooled, and they actually mingled throughout the space. So, they alternated down the aisle. So as that air mixed, you really couldn't tell exactly what was going on until you looked at the data. And then you paint this picture. We literally have the mechanical system fighting itself with one heating as much and one cooling. And the response to this is, this turned out to be a broken heater that was running all the time. If you look even back in August, getting this repaired, bringing this back in line so it's not doing that, and then bringing the temperatures so they're more in line with what we're looking for or what we want. So before we wrap up, we'll cover some quick what not to do. First and foremost, this is something I want to say knee-jerk that we see happen a lot, is the use of portable air conditioners to lower the temperature in a collection space without taking into account the relative humidity or the dew point. And a lot of times we're really, really hot. We need to take care of this. So they'll roll in a portable air conditioner, and giving as an example, so looking at the left, say if we have a collection space, it's 58 degrees, our relative humidity is 54, and the temperature is 77. It's warm for human comfort. We don't want that. We want to reduce that a little bit. We want to break that down, knock that down a little bit. So we'll go in and we'll bring in a portable air conditioning unit. The problem with those portable units is most of the time they do not affect dew point. They will not remove moisture from the air. So anytime we're going to affect that dew point, if we're reducing dew point, we're removing moisture from the air. If we're increasing dew point, we're adding moisture to the air. So those portable units tend most of the time to not do this. So we run those units, if we're running around there, the same dew point, we lower it even to 70 degrees to make it more comfortable. Our relative humidity jumps up to 69. And if we lower that, say, even lower, if we go to 68 or even 66, this gets even higher. It puts us into pretty uncomfortable territory, even dangerous territory for our collections, somewhere we don't want to be. So it's something to keep in mind that many times bringing those portable air conditioners in, using those can cause more issues than we thought. And lastly, also taking into account that building envelope, humidifying or dehumidifying without a proper vapor barrier in a building. If you go into a facility, if it doesn't have a proper vapor barrier and you try to create really tight conditions, and we say dehumidify in the summertime really, really well to say 40%, or we humidify in the wintertime really high, we'll wind up driving salts that are within the brick or stone in the facility out. And if you walk around a stone or brick building and you see this white, almost like white crystals that are on the outside of the building, it's efflorescence. It's the salts and minerals that have been picked up by the moisture traveling in or out of the brick. And it can weaken the brick over time it's something we want to avoid, but it's a sign that we don't have a proper vapor barrier. We're trying to hold conditions within a facility that the facility may not have been designed or may not properly be able to achieve.
Okay, so just to conclude, I hope this has shown how comparing different spaces, including to the outside conditions, and over time and looking at different parameters can help you get a sense of patterns and relationships that can point to causes of issues. And again, it's that communication and documentation that really give data its value and allow us to move forward. So just wanted to thank everyone for joining us, and really do please consider taking the time to complete the brief post-webinar survey. I think there's like 8 questions or so. It's pretty short, but we really do pay attention to your feedback. I hope for those of you who have been present for the other webinars, you can see that we've tried to be responsive to that, and the information gathered helps us to evaluate our approach in this grant and strengthen our educational resources in the future. And so speaking of which, there will be some upcoming workshops that help to build on environmental management and additional educational opportunities. So please stay tuned either by checking the IPI website or subscribing to our newsletter. So I think now we're going to go ahead and take some questions.
I wanted to really quick before we do the questions, wanted to repeat, those of you who are interested, the methodology of the guidebook that I talked about is available on the IPIsustainability.org site there's a resources tab. And on the resources tab, there's 2 guidebooks. There's an original one that was created a few years ago, the IPI's Guide to Sustainable Preservation Practices for Managing Storage Environments. And there's the one we recently produced that is IPI's Methodology for Implementing Sustainable Energy Saving Strategies for Collection Environments. Both are free downloads. On the IPIsustainability.org, plus a few other handouts that are on there as well. So I have one question that do you know roughly how much moisture is added to the environment by a person over time? And I wanted to verify before I just spoke off the cuff, so I verified it while we were doing while Kelly was talking. According to the Canadian National Research Council of Canada, a family of four can emit 5 liters of water a day, and it's an average of 1.25 liters per day per person. So it gives you an idea of how much moisture a person can add. And the human heat gain as well varies from the type of work a person does. But an average, say it has for a restaurant, the average human can add about 240 degrees of heat or 240 BTUs of heat to a space. So you multiply that by whatever your attendance may be, that gives you an idea of how much you can affect. If you have a gallery with 100 people in it, not only heat-wise but moisture-wise can affect the space and what the load is that has to be removed.
Okay. Okay, we had another question about looking at seasonal set points, and relative humidity has gone from 45 to 60%. It sounded like this may not be too high. We were under the impression that this is too high, and we're looking to raise our temperature slightly to lower it. Do you have any recommendations? Unfortunately, this is definitely a situation in which the context, in terms of the type of collection materials and the building envelope and the layout, all of that would definitely play a role. So I'm sorry that there's not a better answer to give to the audience as a whole, but certainly if you're interested in talking through the specific situation and working to try to develop what might be good action steps, we'd be happy to talk with you individually to go through some of those specifics.
A quick question, is there a way to get rid of efflorescence? A quick answer on that is yes. You can always, once it's out of the, out of the stone and on the walls, you can really just, I've seen people just scrub it away, get a brush and scrub it off. It's really, once it's out, it's there. It's kind of been lost from the stone. But our goal is to try, once you see it, to try and work to prevent it from continuing to occur. Try to prevent that moisture transfer where you're losing those minerals as well. And why are dehumidifiers the last resort? What are the risks besides having to remove to drain the water? It goes back about maybe 10 years ago. There was a series of, and there were, by series, I mean 5 or 6. There was not fires that occurred because of dehumidifiers. It was poor compressors that were being made. It was one of those, as our supply chain goes in the modern world, where one company was making compressors for, I believe, almost every manufacturer, from Sears to Home Depot to a whirlpool. So one manufacturer was making a compressor. The compressor turned out to be faulty, and there were a number of fires and close calls that occurred. So it makes us, we're still a little hesitant to recommend humidifiers to people or dehumidifiers to people because of that. Just that fear of, I'd hate to say, you can use a dehumidifier, it's perfectly safe, because there was that risk. There were situations that occurred when fires did happen. Granted, the number was small, but we only have to have one that would really be a tragedy.
I think the other point to make about dehumidifiers is when we've seen them in operation, and it could be different, for other space, for your particular space as well, but it's important to get them sized appropriately for the volume of space, and it's also important to consider how tight the room or building envelope is. So trying to run a dehumidifier in a space that is open to others or that is particularly leaky, it often lessens their impact. So that's another thing to consider, by adding that level of, of energy use and the additional complications of having to drain the water, that sometimes their impact, I'd encourage you to evaluate whether their impact is indeed felt or not. In some instances it is, but in a number of ones it hasn't been. We've also seen issues where dehumidifiers have turned off and the water within the system has grown mold, which has also caused an issue. So I hope that kind of summarizes some of the complications around dehumidifiers, while recognizing that a lot of times they are in use and can be effective solutions for places. So for those of you sticking with us, I think we just had one final question about a good recommendation for how to get outdoor data and overlay it without an extra logger. And I know that this question has a little bit more nuance to it. I will say in eClimate Notebook, which is what the question is directed towards, there is outside data available, so you wouldn't need a logger. You can just import the data directly from the software. But I see from the question that you're concerned about subscription levels and everything. So there are ways to do it. It would just involve archiving a certain data set so you'd be able to pull that up.
Just got a question actually just came in. Can you describe how high MERV filtration stresses the system? The MERV filtration, the MERV rating is the system they apply to for those who don't know, I'm sorry, is the rating they apply to the filtering system, so they know how well or how much particles can be removed from the air as it goes by. The higher the rating, the more particles it's going to block, the tighter the grid or the screen will, if you will, the more it's going to block. In doing so, the more you're going to impede the airflow or reduce the airflow as the air crosses that. So if you go from MERV 8, which is pretty standard for a home filter, basically, to the MERV, I think it's 13 or 14, which they're recommending for coronavirus, your system, the fans specifically, have to be designed to handle that difference, because you're going to have reduced air load, or what they call it, reduced water column across the filter, because that stress, that reduction of airflow is going to cause more strain on the fan. The fan has to run more to push air through the system.
Okay, well, I think that concludes all the questions we have for now. Again, please feel free to reach out at any point in time, or even use the survey response as a chance to ask further questions. We really appreciate you attending these webinars, and so apologize for going over time, but hopefully it's been useful as well, and we look forward to you joining us on future educational opportunities. Thank you very much.